Every game of chess begins in a state of perfect crystalline symmetry. Two armies, 16 pieces each, 64 squares. It looks manageable. But the moment the first pawn moves, the symmetry shatters into a combinatorial explosion that defies human comprehension. By move 3, there are 9 million possible positions. By move 40, we encounter the Shannon number, 10 to the power of 120. To understand the scale of this, consider that there are only about 10 to the power of 80 atoms in the entire observable universe. If every atom in the cosmos was itself a universe, and you counted every atom in those universes, you would still be trillions of orders of magnitude short of the possible games of chess. Yet in the cold, hard logic of game theory, chess is not considered infinite. It is classified as a finite, two-player, zero-sum game of perfect information. Because it fits this rigid mathematical definition, chess is, theoretically, already solved. Every game you have ever played is just a single tiny leaf on a cosmic tree whose root was planted over 1,000 years ago. In 1912, a mathematician named Ernst Zermelo changed the way we look at games forever. He proposed that in any game that is finite, has no element of chance, and where all players have perfect information, there exists a strictly determined outcome. Applied to chess, Zermelo's theorem proves that from the starting position, one of three truths must be absolute. Either white has a strategy to force a win, black has a strategy to force a win, or both players have strategies to force at least a draw. This means that luck does not exist in chess. When you lose, it isn't because your opponent got lucky, it's because you deviated from the mathematical truth of the board. Zermelo's work tells us that if two perfect, godlike computers played each other, the result would be identical every single time. The only reason we don't know that result yet is because the search tree is too vast for our current hardware to reach the bottom. We are like ants trying to map a mountain range by looking at individual pebbles. How do we and how do computers actually navigate this mountain? We use the Minimax algorithm. This is the heart of competitive game theory. Imagine the game as a tree. The current board is the root. Every legal move creates a new branch leading to a new node. To solve a position, we look ahead to the end of the game, the terminal nodes, and assign them a value. +1 for a win, 0 for a draw, and -1 for a loss. As white, you are the maximizer. Your goal is to choose the move that leads to the highest possible value. As black, you are the minimizer, seeking the lowest value. The minimax value of a position is found by working backward from the future to the present, a process called backward induction. If you see a brilliant move that leads to a flashy attack, but your opponent has one specific boring response that forces a draw 10 moves later, the minimax value of your brilliant move is exactly 0. In the eyes of game theory, beauty is irrelevant. Only the forced outcome matters. If a computer tried to calculate the full minimax value of the starting position, the sun would turn into a red giant before it finished the first branch. To deal with this, programmers use a cheat code called alpha-beta pruning. This allows an engine to stop calculating a branch the moment it realizes that path is worse than a previously analyzed move, potentially saving trillions of calculations. However, even with pruning, we encounter the horizon effect. We can't see the forced checkmate from the opening, so we hit a horizon where calculation must stop. This is where static evaluation functions come in. Instead of seeing the end of the game, the engine assigns a numerical value to the current state, measured in centipons. It doesn't just count material, it weighs complex tensors like piece coordination and king safety. These are proxies for truth. We use these heuristic weights to stand in for the actual solution of the game, betting that a position with a higher mathematical score is more likely to be part of the winning line we can't yet see. In broader game theory, we talk about the Nash equilibrium. This is a state where neither player can improve their outcome by changing their strategy, assuming the other player's strategy remains the same. In the 1990s, the world was shocked when IBM's Deep Blue defeated Garry Kasparov. But today, even the best human player would be crushed by a phone app. As engines have evolved, we have seen something fascinating. They are converging on a single truth. When the world's two strongest engines play each other today, they draw nearly 100% of the time. This strongly suggests that the Nash equilibrium of chess is a draw. Some theorists call this the draw death. It implies that chess, when played perfectly, is a struggle that ends in a dead heat. For the theorist, this is a beautiful resolution of a centuries-old problem. For the fan, it's a reminder that the perfect game might actually be the most boring one. For 50 years, chess theory was dominated by Type A engines, brute force calculators that followed human-written rules. But in 2017, everything changed with AlphaZero. AlphaZero didn't use human heuristics. It was given only the rules of the game and told to play against itself millions of times. Using reinforcement learning and deep neural networks, it discovered its own version of game theory. It showed us that some perfect strategies were more aggressive than we thought. It would sacrifice pawns and pieces for long-term positional compensation that traditional engines couldn't calculate. AlphaZero wasn't just calculating a tree, it was sensing the geometry of the board. This shifted our understanding of game theory from a purely search-based problem to a pattern recognition problem. It proved that even in a solved game, there is room for style.